Okay, welcome to the video on sequences. Your objective is you will be able to express arithmetic and geometric sequences explicitly and recursively, and also find the limits of convergent sequences. So a lot of new words there, but we're going to figure out what those mean in just a second. Okay, so sequences, any set of numbers in a specific order. Each element in the set is called a term, and we use a subscript to identify the term we are talking about, right? So if you look at our first sequence here, we're just saying a sub 1, a sub 2, a sub 3. The number down here is telling you which term we're talking about. Here is another sequence. This should actually be number 3 here. Here's another sequence, 5, 10, 15, 20, 25. This is a finite sequence, which follows the same pattern for a fixed number of terms. As opposed to this one, 4, 8, 32, and then all these dots means that it's an infinite sequence, which follows the same pattern forever. We're also given a rule here to figure out each term. So now let's talk about defining sequences. So there's two ways you can define a sequence. You can define it explicitly and recursively. When you define it explicitly, this gives the sequence as a function of the number of terms. Okay, the benefit of this one is you can quickly find any term. If you know the term number, so which term you're looking for, like the 12th term, the 100th term, you can just plug that number in for n and find out what that number, what that term would be. So for instance, for this example, find the first 3 terms of the sequence. Well, I just need to find a sub 1. I would just plug in 1 for n, 2 to the power of 1 is 2, times 10 is 20. If I want to find a sub 2, the second term, then I just plug in 2 for the exponent, and I get 40. And a sub 3, I plug in 3 for the exponent, and I get 80. Okay, to define it recursively, this gives the first term and a function for finding the subsequent terms based on the previous term. So this one isn't as easy to find any term, because any term that you're looking for, you have to know the term just before it, right? So if you're jumping to the 100th term, then you have to find the first term, the second term, the third term, the fourth term, the fifth term, the sixth term, and so on until you get to that 100th term. Okay, so let's zoom in on here. Also, I have a mistake in how I wrote this. We need this to actually say, so you can just scratch this out here. We need it to say a sub n equals a sub n minus 1 minus 5 for n greater than 2. Okay, so what is this saying here? Well, so this first part here is telling us that we can find any term. This is going to give us any term that we're looking for. If we take the previous term and we subtract 5, and that's for all terms that are greater than 2. So why greater than 2? Well, we already have our first term here. This is our first term. And our terms are always going to be whole numbers. We're always going to look for a sub 1, a sub 2, a sub 3. So if we've already found a sub 1, or we're given a sub 1, then the next one to find is 2, and go from there. So let's go ahead and use that. So we have our first term is 57. Let's write this as a sequence. So how are we going to find our second term? Well, this is saying you can find the second term if you have, right, a sub 2 minus 1. Well, a sub 2 minus 1 is the same as a sub 1, right, minus 5. A sub 1, well, what is that? That's 57. So take 57, subtract 5, and we get 52. So the next term is 52. Now we want the third term, so a sub 3. is just, well, you don't have to write this part, but it's just a sub 3 minus 1. Well, a sub 3 minus 1 is a sub 2. So that's why that's the notation for the previous term. So subtract 5. If I need a sub 2, I just found it on the last problem. It's 52 on the last term. Minus 5 equals 47. Right? And so on from there. Because it's saying for all n, all terms greater than 2. So let's also write this as a sequence. 80, and from there. Okay, now let's talk about limits of sequences. So if we do have an infinite sequence, what is the limit? So as n keeps growing, what do the term values approach? So a converging sequence, given the sequence a sub n, as n approaches infinity, the limit is a number. And we call that converging. For diverging sequences, given the sequence a sub n, as n approaches infinity again, so as our terms are increasing, the limit is infinite or non-existent. So infinite or non-existent. So here's some examples for that. Determine if the following sequences diverge or converge. If it converges, give the limit. So here I see the numerator staying the same and the denominator is increasing. So as the denominator is getting bigger each time, the overall number or term is getting smaller. So we would say that this is converging. And then the limit is 0, because these numbers are getting smaller and smaller and smaller and smaller. They're not going negative, they're just approaching 0. Okay, so what's going on here? I can see the numerator is increasing by 1 each time, and the numerator is increasing by 1, the denominator is also increasing. So if we have the term, we could change this into a rule here. If this is our first term, we can think of this as, okay, well, n is the first term, and then the numerator is just n plus 1, right? And if you think back to when we first started talking about limits of functions, you just needed to see what the leading terms were doing as far as the exponents. So I'm just going to focus in on the n and what that would simplify to. Well, since that simplifies to 1, that means it does converge because its limit is a number. So it's converge. And the limit, well, n over n simplifies to 1. All right, for C, we have -1, 1, -1, 1, -1, 1. So it's not approaching a number. It's also not approaching infinity. But in this case, the limit does not exist. So we call this diverging. So this would be diverge. Okay, how about this one? Again, if we have a rule here, right, back on B, I found a rule to figure this out. But here we have a rule. What would those simplify to? Well, 3n over n would just be 3. So this is going to converge. And the limit is 3. How about this one? All right, so we can see that because of this exponent here, the bottom is growing faster than the top. So as we plug in numbers to infinity, since our bottom is growing faster than the top, it's a lot like A here, right? The bottom keeps growing bigger and bigger and bigger, then it means it's approaching 0. So again, we're approaching a number, so this is converge, and the limit is 0. And then last one here. Here, the top is growing faster than the bottom. All right, so as we plug in bigger and bigger numbers, the top is getting bigger and bigger and bigger. So it is approaching infinity. So we say that this sequence diverges. Okay, so we have 2 types of sequences. We have arithmetic and geometric sequence. So let's focus on this one first. So an arithmetic sequence is a sequence whose successive terms, so all the terms that come next, have a common difference. Okay, so something that we're adding or subtracting to each term. So add, subtract to each term. That's how you know it's arithmetic. Okay, here's the explicit formula for arithmetic sequence. Now, you are going to have to memorize this, but if you really understand it and practice it, the memorization of this shouldn't be too hard, because all we have going on here is this is any term that we're looking for. So term to find. This is always going to be your first term. This is always going to be your common difference. Now, if I have a sequence, right, and you have to write this part down, but I have some sequence and I'm starting off with a term here, right, and I want to get to some other term. Maybe I'm trying to find this term here, and I'm adding the same number every time. Again, don't write this down, just follow me for a second. If I'm adding the same number each time, well, repeated addition is just multiplication. So that's why we're going to multiply these two together, and then the n minus 1 is just telling you, well, how many times you have to multiply. So let's erase this. But you're going to multiply by the number of times you add the common difference. And that may seem vague right now, but hopefully once we give this a try, you'll understand that better. All right, so the recursive formula, well, actually, the explicit formula sometimes is harder to remember or to come up with. The recursive formula is probably easier to come up with, but it's not as easy to use, because if I need to find some term far away, like the 100th term, it's just harder to get there. So for the recursive formula, you just have your first term, right? And then in this case, you have term to find, and you're taking your previous term and just adding on the common difference. All right, geometric sequences. So this is a sequence whose successive terms have a common ratio. Okay, so in our explicit formula, again, this is our term we're trying to find. So term to find. This is our first term. Now we have in here our common ratio. And then we have that it's being raised to a power. So why does that make sense? Well, back here, a common ratio is just when you multiply or divide by something. So we'll just say multiply, because if we divide, we're actually going to multiply by a fraction. So multiply. Okay, so here, again, you don't need to draw this thing. But if I'm multiplying by some number each time, multiply, multiply by a number, multiply by a number, well, repeated multiplication, right? We start with our first number, whatever this is, and we want to get this number here. If I repeatedly multiply, then I'm just raising something to an exponent. I'm taking my common ratio and raising it to some exponent. And that exponent is determined by, well, how far away are we trying to get? What's the term that we're trying to find? So this is going to tell you how many times you have to multiply by the same number. So that number there means that you raise to how many times you multiply by the common ratio. And hopefully, if this isn't making sense now, hopefully once we do some examples, it'll make more sense. All right, so coming down here, this is more straightforward. You have your term to find. You have your previous, and then you're just taking your previous term and multiplying it by the common ratio. All right, let's pull that all together now. Make sure you have that all written down to refer back to. But let's pull that all together by actually doing some problems. Okay, so for the following sequence, A, determine if they're arithmetic or geometric. B, write the recursive formula. C, write an explicit formula. And D, find the first three terms of the sequence and the 41st term. All right, so A. What we're looking for is the change between each of these. What's happening? We're either adding, subtracting, or multiplying something for each of these. So negative 12 minus 1. To work backwards, you can always just divide or subtract and see what happens. So if I go negative 1 minus a negative 12, then I'm getting 11, right? So now let's check and see if that works. So I think that maybe it's add 11 each time. So if I take negative 12 and add 11, I do get negative 1. If I take negative 1 and add 11, I do get 10. So I'm going to say that is add 11. If I want to check to see if there's a common ratio, I would do negative 1 divided by negative 12. Well, that's 1/12, right? So negative 12 times 1/12 does give me negative 1. But does negative 1 times 1/12 give me 10? No, it does not. So it is definitely arithmetic. I'm going to erase this. And I didn't put this in the directions, but let's go ahead right now and define what the common difference is. So we have it written down. The common difference is 11. All right, so part B says write the recursive formula. So the recursive formula is the one that I said was easier to write because you take the first term, so A sub 1 is our first term, and we're given that. We can see that it's negative 12. And then we know, okay, you just take the previous term and you add 11 each time. So that means take any term, take the previous term. This is just a notation, right? This is going to say that stay the same each time. And then add 11, right? So when we're writing this, you can make a note that this part stays the same for every time you write this. And then this is just your common difference, which I'm going to abbreviate here. All right, so C, write an explicit formula. This is a little bit harder to write, but if we look at our directions up here, we know that we need to have A sub n, so some number equals A sub 1, well, we know what that is, it's negative 12, plus the common difference is 11, and then we need n minus 1. In this case, this is the part that stays the same. For every time we write this, stays same. And it's these other parts that you have to change. So this stays the same. And you can see that this is just a function of n. All right, last thing here tells us to find the first three terms. Now I'm going to change that. I'm going to make it say the next three terms because we already have the first three terms. So let's go with the next three terms instead. Okay, so for the next three terms, that's easy. We can use either one of them, right? Because our recursive formula says take what you have and then just add 11 each time. So when I go to do that, I have D, right? I'm going to take the previous term and I'm just going to add 11 to it. I'm here, I add 11, I have 21, I add 11, I have 32, I add 11, and I have 43. That's using the recursive rule because the recursive rule just says take the previous one and add your common difference. Now, if we want to find the 41st term, using the recursive rule would take a long time. So instead, let's use our explicit rule. So we're looking for the 41st term. So a 41st, and that says our rule tells us to go negative 12 plus 11 times n. Well, what's n? N's 41 minus 1. So now following order of operations, I'd have 41 minus 1 is 40. Then I'd have to multiply the 11 and the 40 together, which gives me 440, and then add a negative 12. So our 41st term is 428. All right, let's try this one. So we're looking for its arithmetic or if it is geometric. So if I were to subtract 25 minus 50, I get negative 25. So then I just need to see if that's the pattern here. I'm going to zoom in. Am I adding a negative 25 each time is the question. So negative 25 would get us there, but then when I take 25 and subtract 25, that does not get us there. So instead, let's see if we're multiplying something. So if I take 25, divide by 50, that is the same as 1/2. So let's see if 1/2 is how we're changing, multiplying by half, 1/2 is how we're changing each time. So 50 times 1/2 gives me 25. Then I multiply by 1/2 again. I do get 12.5, multiply 1/2 and again, and I do get 6.25. So this is a geometric sequence, which means there's a common ratio, and that common ratio is 1/2. Okay, so for B, we need to write our recursive rule. Now for the recursive rule, we just say where it starts. So here for this sequence, we have a sub 1 equals 50. And then we just write the rule. So for any term, a sub n, I take the previous term, a sub n minus 1, and each time I'm going to multiply by 1/2. Okay, so that is our recursive rule. Now let's find our explicit rule. For this one, we're going to say any term, but now we're going to give what we're starting with, and we're going to multiply it by our common ratio. And how many times? Well, that is determined by our exponent, so n minus 1. So remember, common ratio is we're just repeating multiplication when we're coming up with a sequence that has a common ratio. So when we repeat multiplication over and over and over again, that's the same as using an exponent. And so this just tells us how many times we're going to multiply by 1/2. So hopefully that'll help you remember this formula. Okay, so then lastly, let's come up with our terms. So the next three terms, 6.25, I take the previous term, I multiply by 1/2, and I'm getting 3.125, I multiply by 1/2, and I'm getting 1.5625, multiply by 1/2, and I'm getting 0.78125. And now for the 41st term, I'm going to use my explicit formula. So 41 minus 1, and I get 50 times 1/2 to the 40th power. Now here I'm getting such a small number that I'm going to actually write it in scientific notation. So I got 4.547 times 10 to the negative 11th. Okay, there you go. Those are your notes, and I will see you in class.